Hey everyone, I'm Becky, your science tutor, and today we're digging deep into the world of metal extraction. So if you've ever wondered how we get useful metals like iron, aluminium and copper from rocks in the ground, well, it's not just as simple as digging them up. There's some serious chemistry involved. And in this session we're going to look at different methods of metal extraction, from using the blast furnace to electrolysis, and we're going to link this to how the reactivity of the metal plays a role in the process. So let's get started. Now, most metals are not found naturally in the ground. There are some, such as silver, gold and platinum. Because they are unreactive metals, we find them what we call native in the ground. If you know where to dig for them, you can find pieces of pure metal such as gold in the ground. However, most metals are combined with other substances because they are slightly more reactive, and therefore they react and they bind to other minerals, etc., that are in the ground. And these are called metal ores. And we've got to get that metal out of that ore. And the extraction method depends on the reactivity of the metal. So in the last session we looked at how reactive these metals were, how we could order their reactivity, and now we're going to have a look at how that excuse me links to how we extract them. Okay, so first of all, let's start by defining the term ore. So when you dig up this rock and minerals and everything else that's there, when you're extracting this ore, we only class the stuff that we've dug up as an ore, and this is a common exam question of what is an ore. It's a metal, so a metal ore is a rock that contains enough metal to make it profitable by going through that extraction process. So basically, however much it costs you to do the extraction, whether that's a blast furnace or electrolysis, you've got to look at, well, how much is it going to cost me to do it, and how much am I going to be able to sell that metal for? Am I going to get enough metal out of the ore to make me a profit? Okay, so an ore. Is a rock that contains enough metal to make it profitable to extract. Okay, so it's going to cost you more money in the process of doing the extraction than what you're going to get back when you sell the metal, it's not going to be worth doing. Okay, now in many cases we find that metal combined with oxygen, because obviously there is a plentiful supply of oxygen out in the atmosphere, and if the metal is relatively reactive, it will react with the oxygen, and we find lots of ores that are a something oxide. So for example, we've got an aluminium ore that is called bauxite, and that is basically aluminium oxide. And when we look at electrolysis in a future session, we'll look at how we extract that aluminium from that aluminium oxide. Okay, so we're going to have a look at what we're going to term oxidation and reduction. Now, if you are a higher level student, you may have heard of oxidization. Let's put in two words together, of oxidation and reduction in terms of electrons. Now we need to just be very clear that this is a different meaning of the word. I know it's not helpful, it gets a little bit confusing, doesn't it? And so this is when we're talking about oxygen, okay? So oxidization can be defined as the gain of oxygen. So simply the metal gaining oxygen, that means that that metal has become oxidized. Now it can be an element or a compound. We're talking about the extraction of metals, so we're just going to refer to the metals as the elements in this session. And if we have a look at those examples, magnesium reacting with oxygen forms magnesium oxide, copper reacting with oxygen forms copper oxide, and these are examples of an oxidation reaction. It's gaining the oxygen. The reverse of that is reduction. So reduction is basically removing that oxygen from that element or compound, or in our terms it's going to be from that metal. So the reduction is the loss. Okay. So if we have a look at the examples, if we have copper oxide, and ultimately what we want to do is to remove that oxygen. So let's just highlight a few key bits. So here we've got the oxygen in the copper oxide, and we want to remove that because what we want to do is we want to get that copper on its own. This is a method of extracting that metal from that ore, so they oxidize while they're out there in the environment, if you like, in the ground. And when we bring them in, we will want to see, can we reduce them to get rid of that oxygen so we've got that pure metal on its own that we can bend, shape, alloy, do whatever it is that we're doing with it before we sell it on. So what we want to do is we want to get rid of that oxygen. And the way that we do that is we combine it with carbon. And so this is where the reactivity series comes into play again, and we'll look at this in a second. Now if carbon is more reactive than the metal it is binded to, what will happen is that the carbon will remove the oxygen from the compound, and therefore we're going to get left with a copper on its own. So if we look as well here, we've got zinc. So zinc is binded to the oxygen, carbon comes along, steals the oxygen, and poor old zinc, but luckily for us, is now left on its own. And therefore we can do whatever it is that we need to do. Smelt it, remold it, alloy it, whatever it is that we're doing with that metal before we sell it on. Okay, so oxidation happens when the metal's out there in the environment, and then what we're looking at is, well, how are we going to extract that? And reduction is one method of extraction. Okay, so let's link this to the reactivity series then. So when you look at the reactivity series or the reactivity of metals, you'll often see that carbon is labelled on there. Now yes, carbon is not a metal. That carbon is there as a reference point for us to be able to look at and say, okay, well, is carbon more reactive than my zinc oxide that I have? If so, I can extract it using carbon reduction. So that would be my extraction method. Okay, so if we go into a little bit, let's formulate a chemical reaction, look at what it is that is going on. Right, so let's dig a little deeper then into iron. So iron oxide, which is just the ore of iron, so it is oxidized again while being out there in the atmosphere. This can be reduced, so this is removing the oxygen, because if we just go back to it, iron is here, carbon is more reactive than iron, and therefore it can undergo carbon reduction. So what we do is we take that and we combine it with carbon in something called a blast furnace, and you can see here on the other side that here we've got a blast furnace. So this is done on a huge scale within industry, and we can see that iron, carbon comes along, it is more reactive than the iron, and so the iron is displaced. carbon bonds with the oxygen to form carbon dioxide, and iron is left on its own. And so therefore we can undergo carbon reduction when we need to extract iron. So coming back to our little reactivity series, okay, let's just label this up. So if we are under carbon, these metals can be extracted by carbon reduction. However, if the metal is more reactive than carbon, we need to choose an alternative method, and that method is electrolysis. And there will be more to come on electrolysis in future sessions. So the reactivity of the metals depends, the extraction of the metals depends on their reactivity, or the reactivity dictates which method we would use to undergo that extraction process. Okay, so there we go, there's our little reactivity series. And when we get to the sessions that are about electrolysis, you will often see on there that this is extended a little bit further, and you might see at the bottom like gold, silver, platinum sort of labelled, and it might say that they're native, they're found naturally or purely in the ground. So you'll see a slight variation of this reactivity series. But if we're reactive metal, we need to use electrolysis. If it's less reactive than carbon, we can use carbon reduction to undergo a displacement reaction and leave that metal on its own. Okay, so as always, let's have a look at some questions. How are you going to get asked this in an exam style scenario? Okay, so we've got iron is extracted from iron oxide in a blast furnace. The equation for one of the reactions in the blast furnace, so it's given as our iron oxide. So we can see there we've got carbon monoxide, and then what is it producing? Complete the word equation. Okay, so we've got 2Fe, so we're simply producing iron plus 3 CO2, which is carbon dioxide. And it is 1 mark for each correct product that you've named. Oxygen is removed from iron oxide in the blast furnace. The iron oxide is reduced. Okay. Oxidized is adding the oxygen, reduced we're taking it away. I was thinking if you're reducing something, you're making it smaller. If you're taking the oxygen away from it, you're going to make that compound smaller. However it sticks in your mind. Okay. Cans for food and drinks are made from steel or aluminium. The main metal in steel is iron. Reacting iron oxide with carbon produces iron. And again, it's asking us what type of reaction is this? It is a reduction reaction. But aluminium cannot be produced by reacting aluminium oxide with carbon. Why does aluminium oxide not react with the carbon? And that is because it is, excuse me, the aluminium is more reactive. Now we've just got to be careful of the wording in this one, because it says that aluminium is less reactive, or we've got like the old switcheroo that carbon is less reactive, meaning that aluminium is more reactive than carbon, and therefore it's that second one down. Oops. Okay, on to our sort of medium level questions then. So here we've got what is an ore. So this is the definition that I was talking about earlier. So an ore is something that contains enough metal so we're identifying it's got enough metal for 1 mark to make it profitable to extract for the 2nd mark. And that's for mark number 2. Some metals are obtained by removing oxygen from the metal oxide. What name do we give to this chemical reaction? That is our reduction. And give one metal which must be extracted from its melted ore by electrolysis rather than using carbon. If you just think, what's the most kind of reactive metals you know? Think about group 1, they're pretty reactive. So anything out of group 1, potassium, sodium, lithium, calcium, magnesium. I know calcium and magnesium are in group 2, but they're still highly reactive metals. Any of those would get you the mark there. Okay. So here then we've got a little bit more about an actual blast furnace and what is going on. Okay. We've got, you know, similar sort of questions, but you can see now they're a little bit higher in level because here we've got to complete the balanced symbol equation, etc. So this is a mid to high level question. So meaning of the term ore, bit stingy on marks this one, but it's the same as we talked about earlier. Contains enough metal to make it profitable to extract. Okay, and then we are asked to complete and balance the equation. So here we've got iron. Remember we were given this the other way around in the low level question, weren't we? When we had to write the words. Now we've got the words, we've got to write the symbols. So iron is Fe and carbon dioxide is CO2. And then we've got to balance them. Okay, so if we have a look at this side, we've got 2 ions. So we're going to need at least 2 iron over here. We've got 4 oxygens over on this side. So we've got 3 on the iron oxide, 1 on the carbon monoxide. So that's 4 oxygens. So if we put a big 2... Let's just think about it a second. If we put a big 2 in front of it, that's going to give us 2 carbons and 4 oxygens. But then if I need to multiply up my carbons, if I put a big 2 in front of that, this is where it gets a little bit annoying, balancing equations, isn't it? Because if I put 2 in front of that, that now gives me 2 carbons, but 2 oxygens, which gives me 3, 4, 5 oxygens. And that isn't going to work. What I need is I need a multiple of 2. Okay, so how about if we try 3 carbon monoxide? That gives me 3 carbons and 6 oxygens overall. Put a big 3 in front of that. Let me get rid of those little numbers out of your way so that you can see where they've come from. So in terms of that question, you get 1 mark for correctly putting the symbols Fe and CO2, and your second mark is for the correct balancing. Part 3 is name this type of reaction. So this is simply our reduction. And then we've got a little bit more information about the blast furnace. So steels are produced from molten iron in 2 stages. We put oxygen into the molten iron in the blast furnace, and then we add other metals to make different steels. In stage 1, suggest how oxygen removes most of the carbon from the molten iron, because we've used carbon to extract the iron, but now we've got that carbon in there. We need to get rid of that carbon. So if we react it with oxygen, we're going to form that CO2, and that CO2 will basically leave that reaction and leave us with iron on its own. So let's pop that into words. Okay, so we'll say that the oxygen reacts with the carbon to form carbon dioxide. just can't quite fit the last couple of letters on. Still not far enough. Oh, it's back. Carbon dioxide. There we go. And then the final question, sorry, let me just budge that back down. Okay, so it says use the reactivity series of metals on your data sheet, that's the sheet that you've got with the periodic table on, to help you answer the question. It says why is gold found mainly as a metal itself in the earth? So why is it basically found on its own? This is because it's unreactive. Yeah, and you'll find that at the bottom of your reactivity series. One of the reactions involved in producing zinc is represented in the equation. So we can see that we're using carbon extraction. Why can carbon be used to extract zinc? So that carbon is more reactive than zinc. It's an example of a displacement reaction. It will pinch its oxygen. And then our final question, sodium is one of the most abundant metals on Earth. Explain why sodium was not extracted until 1807. Basically, that sodium is far too reactive. It's just going to bond and react with other things. Yeah. We needed to use electrolysis. We know that now, don't we? That it's electrolysis, but we had to wait for the discovery of electricity. So all that was happening is when they were extracting it, it was just bonding to something else, and so therefore we were never getting pure metal on its own. So we'll just pop that in as an answer. So we want to say that sodium is very reactive. And then you can say that like it needs to be extracted by electrolysis, or we can say that we had to wait for the discovery or the generation of electricity. Okay, and as I say, you will learn more about electrolysis and how we actually use electrolysis to extract those metals in some later sessions. Okay then guys, hope you found that useful. As always, if you have any questions, please do reach out, and I'll see you next time.